Okay, hello folks. Welcome back to our offsite learning. I hope you all had a great spring break. So before we finished up Unit 2 altogether, right? That was the electricity and magnetism unit. We are now going to move on to Unit 3 or Unit C, okay, which is all about electromagnetic radiation or EMR. So to start out, you will need the notes package for Chapter 13, okay? That's the first chapter in our new unit. It'll be in the Google Classroom. So let's jump right in. Okay, so to start out this new unit, we're going to have a bit of theory right at the beginning. In general, there might be a little bit more theory in this chapter than in previous units, okay? And so as I've said, right, this chapter is all about electromagnetic radiation, okay? You might be thinking, what is that? You've actually learned about it before, okay? We're going to get there. So as you might be putting together, you can see that we're starting with a brief history of theories about light. So light is a form of electromagnetic radiation. Okay, so to give you a very quick SparkNotes version of the kind of history of the theories here, we essentially had two main competing models. Okay, there was the particle or the corpuscular model. You can just call it a particle model, but know that word corpuscular if you see it. Okay, which essentially says light's made up of small particles, little actual particles, little balls of stuff, I guess, right? And then there was the competing model, which was the wave model. So essentially the story of the history of theories about light is particle or wave, okay? So light is some kind of wave, as the name suggests. So is light a particle or is light a wave? Stop and think about that. Do you know the answer, right? It might not be something we think about too much, but light is a thing. So this was a big question for a lot of the history of physics. Okay, so let's start with the particle model. So people had done thinking about light, about its behavior, a lot of people, but in Western science, but the first time that we kind of start to majorly sit down and say, okay, we know how it behaves, but what is light is often kind of credited to this Renaissance period, right? And so we started out kind of the strongest theory that started out was that light was a particle. Okay, so this was old, it treated light as a particle, obviously. Now, this was a very popular theory for a very long time. You know why? Because one guy supported it, and that guy just happened to be Isaac Newton. I shouldn't say one guy supported it, a lot of people supported it, but because of this guy supporting it. Newton was, you got to remember, one of the greatest minds of his time, right? Still to this day, pretty much everything you've learned in physics has come from Isaac Newton in some form or another, right? In fact, you would even maybe call all of what you've learned so far in physics Newtonian physics, with the exception of last unit, right? But up until chapter 9, everything you've done is often just called Newtonian physics. That's how big of a deal Newton was, right? And people knew it. He was respected for a good reason. He was brilliant, okay? But this particle theory stuck on for a really long time because he supported it. And if he put his stamp of approval on something, people listened. Okay, so why did he like this theory? Well, light did a lot of things that particles do. Okay, for one, it travels in straight lines. Okay, so when you throw a ball, that's a particle, it just travels in a straight line, if you're in space anyway, right? And gravity's not there to pull it down. Imagine for a lot of these pool balls or billiard balls, right? These are a good way to kind of imagine how we were thinking about light as a particle. Because like a particle, well, it is a particle, a billiard ball will reflect off of surfaces, right? If you shoot it at an angle, it hits a wall, it reflects perfectly. So light does that. Light reflects off of surfaces and it can be absorbed, just like a particle. A particle can be absorbed by something. Okay. Now, to be honest, this was kind of weak, right? Not the best reasoning on Newton's part because waves do this too. So really, that doesn't say they're definitely a particle. It doesn't say they're not a particle, but waves do it too. So not the best evidence. Okay. Now here's the big one. This is the big reason that the particle model actually does seem pretty strong, right? Particles can travel through a vacuum. Again, a vacuum is just empty space. Okay. The only waves that we knew about at the time, and maybe even the only waves you can think of, were mechanical waves. Those are the waves we covered in physics 20 for the most part, right? I think we had a brief discussion on non-mechanical waves, but for the most part, all we know about are mechanical waves. Well, mechanical waves are, what are they at the end of the day? They're just the movement of energy through a medium. So again, when I say a wave, if you picture a water wave, the water is not the wave. The wave is the energy moving through the water. Take away the water and do you have a wave? No, right? So waves need a medium to move through. That's the whole thing a wave is. It's energy moving through a medium. So if light is a wave, how could it travel through empty space? There is nothing in space to vibrate. There is no water. There is no air. There is nothing in space to vibrate. So, how can we see the sun? How is light reaching our eyes from the sun if there's nothing in space to vibrate through, if light's a wave? Now, if light's a particle, that's no problem, right? If light's a particle, particles can move through space, right? Asteroids are hurtling around out there right now because they're particles. They're not waves. They don't need anything to travel through. So this idea, all we knew about, the only type of wave we knew about was a mechanical wave, the ones you learned about in Physics 20. They need something to vibrate through. Okay, so right now you might be thinking, okay, well, sounds like light was probably a particle. Maybe Newton was onto something here. Sounds like he had it down because of that point. However, scientists began to make observation of lights behaving in ways that it could only be explained if light were a wave. So we started to notice some things that said, particles don't do this, okay? So Christian Huygens, I've never been quite sure how to say his name. Everyone says it differently. I'm pretty sure it's Huygens, saw that light diffracted around obstacles or through slits. We're going to go to that more depth for now. We're just going through a brief history, okay? Now, diffraction is a result of, here's a word from Physics 20, constructive or destructive interference. Do you remember when we talked about that? Did we talk about it when we were talking about matter and particles? No, only waves interfere with each other, right? That's where they add up. So, for example, if a crest meets a crest, it'll be 2 times the crest high, right? Or if a crest meets a trough, they'll just cancel each other out. That would be destructive interference. So you got no wave at that point, okay? So no doubt about it, Christian Huygens, when he did this, he saw constructive and destructive interference happening. He was getting patterns that would only be explained by that. Particles do not interfere. Waves interfere. So that was already, oh, geez, how do you explain that if light's a particle? Okay. Then Thomas Young came along and did something called the double slit experiment. We're going to go into that in depth later as well. Okay. This really was the final nail in the coffin for the particle model of light. There was zero way to explain how a particle could do what we saw in Thomas Young's double slit experiment. What was the double slit experiment? It was essentially just another way to show constructive and destructive interference. Okay. But very clearly this time. Essentially turned light sources into 2 point sources. That's the double slit part. Essentially pass light through 2 slits. By passing it through 2 slits, you turn it into 2 point sources. Remember, 2 point sources, well, that just means you have 2 things that are making waves now, right? And those waves will meet up with each other from those 2 different sources, and depending on how they meet each other, they will either constructively or destructively interfere. Particles wouldn't do that, right? If you have a bunch of particles flying out from 2 point sources, they're not going to interfere with each other. They're just going to go wherever they go. Okay. And so clearly an interference pattern. That was it. There was no longer a way to explain this. Honestly, though, people still held on to it for a long time just because of the respect that Newton had, right? When he when he put his name on something, again, people really had a hard time letting that go. And he kind of fought pretty much his whole life that light was a particle. There was one kind of turning point where science finally fully rejected it, and that was that it was shown that light could be both reflected and transmit through something. So in other words, picture a lake, right? Light can both bounce off the lake to your eye and you can see a reflection of something, but if you're underneath the lake, light can still make it through to you. So light can both reflect and penetrate something, which a wave can do. Okay, parts of a wave can make it through and some of it will get reflected off. However, a particle doesn't do that. A particle either reflects or it goes through, right? And when really Newton lost this battle is he tried to explain that and he basically said, I don't know, particles decide if they're going to bounce off or if they're going to go through. They have a fit is the word he used, right? And it was not a great explanation. And so most people kind of said, okay, Newton, you did a lot. Awesome. Thanks, bud. But seems like light's a wave. Okay. So might be saying to yourself now, but still, how did it travel through space? Right? All this stuff says light has to be a wave, but remember, waves, as we understand them at this point anyway, shouldn't be able to travel through empty space. Okay, so we're gonna actually a big bulk of today is gonna be figuring out how this was actually overcome, this problem. Okay, so we are going to go into this, but just the kind of a brief overview right now. A scientist, James Maxwell, solved this problem, okay, by applying mathematics. It was purely a mathematical solution at first that described wave motion to the equations that govern electric and magnetic fields. So this is unit 2 coming back up, okay? Now, the resulting equations not only explained a lot of stuff, but they also predicted many things that are vital to our understanding of light, electricity and magnetism, and literally physics itself. Okay, these things revolutionized physics. There's no way to oversell the importance of these equations. Okay. Now, one of the big things, what was the big deal about them at this time anyway? There's a lot of big deals, but at this time, what was the big deal? It included the existence of waves that were non-mechanical. So Maxwell's equations predicted waves that were non-mechanical. What does that mean? They don't need a medium to travel through. These were electromagnetic waves. We're going to dive into that now. We're just going through a quick history, right? And then things changed again. So not that these guys were wrong, because they weren't. Okay, things are going to get a little bit weird next chapter. So the next big model was the quantum model, okay, and it actually features a bit of a return to the particle model while still keeping the wave model in an interesting way. Okay, things are about to get a little funky for us next chapter. But the gist of it is that light and other electromagnetic radiation can act like a particle in a collision. So collision, hey, back to chapter 9, back to unit 1, okay? That was weird. Waves don't act like particles in collision. So to explain this, when we get to explaining it, which we're not this chapter, but when we get there, it's actually going to require our first glimpse into the world of what we call modern physics. Everything you have learned so far is classical physics. So our first baby dipping our toe into what we call modern physics to understand even the basics of how we currently understand light. Okay, so there's the brief overview of the entire history. So you do kind of need to know the basics of the models, the basic experiments that kind of proved them or disproved them or supported them or whatever, okay? That's why we are spending time on this. But let's now just say, let's back up a bit, okay? We did the whole history. Let's back up. Where are you right now? So in theory, I know it's probably been a while, but in theory, you roughly understand light about where someone would be before Maxwell's work. Okay, so you've learned that light is a form of energy. Okay, in previous science classes, you should have covered that light's a form of energy. It's a wave carrying energy anyway. Okay, you've learned that light is a wave. Okay, grade 8 optics, you'd learn that light's a wave, that it's a form of energy. Now, maybe you didn't learn this, you shouldn't have been taught it, but you've probably only ever really thought that whatever light is, it's just light, right? In other words, whatever type of wave light is, because right now you quote unquote know that light is a wave, but it's the only type of whatever wave it is, right? There's light waves. There's light waves, and light waves are light waves, and that's a light wave, okay? Now again, like we said, okay, we're going back to where were you when you stepped foot into this classroom? You learned in physics 20 that waves need something to propagate through, right? We're backing up. So space being empty is a big problem, as we saw. Let's jump into it now. How was this problem solved? Okay, now this guy here, I've heard it said before that if you were to name the top 3 physicists, who would you name? Well, everyone right away would say Albert Einstein, Isaac Newton, and then on the third one, they kind of go, ooh, I don't know. There is a very strong argument to be made that this guy deserves that number 3 spot. His work led to some of the most important advances in physics ever made. And we should have known it because what a last name, right? That's a kind of last name you just hear and go, wow, that guy's sick. Okay? And I know what you're thinking. The answer is yes, he is my dad. Okay, so we now go. So let's take a look at this James C. Maxwell guy. Okay, what did he actually do? Well, he kind of started off where we finished off last unit, right? So this is good. We're kind of at the point where Maxwell in the world of physics was in understanding, and we're going to now look at what next. So this is going to require a bit of a reworking of our understanding of last unit, actually. Okay, so the first thing he did is he took a look at Ørsted's work. Now, Ørsted, you might remember, showed that a current produced a magnetic field. Now, Maxwell did some nitpicking that at first you go, okay, guy, whatever, right? But he was not convinced that this electric current was directly producing a magnetic field. That seemed weird to him, right? So why is electricity affecting a magnetic field? Only magnets should do that. Now, what he didn't have a problem with, of course, because why would it be a problem, was that an accelerating electric charge causing a change in an electric field, that was no problem. Of course, an electric charge changing an electric field, why would that be an issue? We know an electric charge has an electric field, so if you make it accelerate, that's going to be important. If you make it accelerate, well, yeah, that electric field is now changing, right? It's in non-uniform motion. So of course, yeah, no biggie there. If you accelerate an electric charge, it should change the electric field. So that was his kind of first thing. He said, I don't know about this, Orsted. Why would a changing electric charge produce a changing magnetic field? So we're going to build up. Now he looks at Faraday's work. So remember Faraday's law, a changing magnetic field induces a current or a changing electric. So remember Faraday's law showed that a changing magnetic field would produce a current or a changing electric charge. Okay, but again, Maxwell kind of said, well, magnetic field, electric charge, why are they affecting each other, right? As we know, they are related, of course, they are related, but he said, why directly? Okay, why is this directly causing a change? So why is a magnetic field directly influencing an electric charge? He didn't doubt the evidence. He said, it seems that something is happening, but he said, why are we sure that it's directly happening? Okay, it would be like Orsted and Faraday said, I drove to work today, right? And Maxwell would say, well, hang on, you drove here? Well, your car's not parked here. It's out in the parking lot, right? And was your car parked in your bedroom and you got up and got into your car? So you didn't drive here, right? You walked to your car and then you got in and then you drove to the parking lot and then you got out and then you walked into work. But you didn't just drive here, right? And Orsted and Faraday would roll their eyes and they say, okay, Maxwell, sure, I guess, right? But this was going to be really important. It turns out that walking part ends up being a big deal. So again, Orsted had no problem with a moving magnet causing a change in a magnetic field, right? Magnet, magnet, sounds good. Electric, electric, sounds good. What ends up being the point of this, right? Was Maxwell just being annoying? So this tiny tweak is going to make a big difference. He said that electric currents only affect electric fields, right? They don't directly produce magnetic fields. They might produce them indirectly, but they don't lead straight to a magnetic field. You might get in your car and drive to work, but you didn't directly drive to work, right? First, you had to walk to get into your car. Okay, moving magnets only affect magnetic fields. Again, they don't directly produce a current. Indirectly, sure, they'll lead to a current, but maybe they don't directly. So then he used, this is important, he used a capacitor, which essentially just changes the electric field, okay, without the motion of charge, to show that a changing electric field on its own without a current could produce a changing magnetic field. Then what did that changing magnetic field do? It produced a changing electric field. Notice field is bolded and italicized here. The field part is important. So in other words, no, a changing magnetic field does not cause a current to change, but it can cause an electric field to change, right? An electric field to change. And no, an electric current moving does not cause a magnetic field, but an electric field changing could cause a magnetic field to change. So the fields do affect each other, right? They don't directly influence the current or the magnet, but the fields can. So in other words, changing magnetic field, changing electric field, no problem. Changing an electric field, changing a magnetic field, no problem. All right, so what's your point, Maxwell? Well, his new explanation of Orsted and Faraday's observations, a slight tweak again, but an important one. So no longer does an electric current directly produce a magnetic field. Rather, an electric current produces a changing electric field. And then this changing electric field can produce a changing magnetic field. Okay, now no longer does a changing magnetic field directly produce an electric current, right? But a changing magnetic field can produce a changing electric field, right? And then that changing electric field can induce an electric current. Pause here for a second and think about that. An electric field, could that induce a current? Well, yeah, of course. What's an electric field? It's just kind of a sphere of influence on a charge, right? If you put a charge into an electric field, it will move. So if we have a magnetic field that produces a changing electric field, well, that electric field can now produce a change in our charge that's flowing through a conductor, aka make a current, right? All right, so maybe you're thinking, what does this have to do with light? This Maxwell guy sounds like he would have been really annoying, okay? Here's the thing. So, what's the big deal? Okay, think of a metal detector. Now, we didn't go over this a lot last unit, but it is just another example that is often used to kind of talk about Faraday's law, to talk about Faraday and Orsted's kind of work, right? So, how does a magnetic field, how does a metal detector work? Really quick, let's go over that, okay? Essentially, what you see here is there's a pulse of current, right? That causes current to kind of go around here. You can see, so, right, that's all that's happening. If you take your right hand and look, you will see that, okay, that current should induce a magnetic field with your right thumb pointed straight down. And then if there's metal there, right, well, now you have a changing magnetic field coming at a conductor, a piece of metal that's a conductor, right? And so a changing magnetic field induces a current, Faraday's law, right? And Lenz's law should be in the opposite direction to resist that change in that magnetic field. So the induced current would be the other direction, which produces a magnetic field up, which, hey, that magnetic field will now induce a current here, right? It's just an application of Oersted, Faraday, and Lenz's law, kind of all at the same time. So how's it work? If we look at it as we did in chapter 12, so put your chapter 12 thinking caps on. We have a change in current in our detector, produces a changing magnetic field, that's this thing here, right? Which leads to a change in current in our metal, right? Which of course then change in magnetic field and blah, blah, blah. But that's what's really happening. So how does it work? Why does it detect metal but not detect not metal? Because if you don't have a conductor there, change in current in your detector leads to a changing magnetic field, leads to nothing. Okay, works great. Sure, for chapter 12. But now let's look at what the implications are of Maxwell's work here. Okay, we have a changing current, an accelerating charge. Okay, now as Maxwell said, that doesn't directly produce a magnetic field, right? No longer does it directly a changing current create a magnetic field. It creates a changing electric field, and then the fields can affect each other. So then, yes, that electric field changing can lead to a changing magnetic field, and then that changing magnetic field can lead to a changing electric field, and then that can lead to a current if there's metal there. Cool, okay? Great, so again, you're thinking, so what, right? What's the big deal? Same result in the end. However, here's where things get interesting. What if there is no metal to be detected? Well then, okay, you have your changing current in your metal detector, which leads to a changing electric field. Sure, no problem there. And now Maxwell said that the fields can affect each other, so you get a changing magnetic field. But hang on, what does a changing magnetic field lead to? A changing electric field. And what does a changing electric field to? A changing magnetic field. And this goes on and on and on and on forever. You have a changing electric field leading to a change in a magnetic field, leading to a change in an electric field. This goes on and on and on and on and on. There's no reason for that ever to stop. It's a self-feeding, self-propagating cycle. So what does it look like when an electric field induces a magnetic field, which induces an electric field, which induces a magnetic field, which induces an electric field? Well, let's just think about it. We have here an electric field that keeps kind of changing, and then that keeps changing, and as a result, changing the magnetic field, right? Or vice versa, however you want to think about it. And so on this axis, okay, on this axis here, you have it going kind of up, down. This is the axis that's flat that's flat with the page, right? And so the electric field changes, but every time it changes, it causes the magnetic field to change. Now, as we know, they're going to act perpendicular to each other, right? And so at a 90-degree angle, the magnetic field is also changing. This one is kind of coming at you and then going away from you on a bit of an angle, okay? Which way are they moving though? Because this one, they are moving, right? As the changing electric field gets larger and stronger, or gets stronger and weaker, and then stronger again, and then weaker again, and then stronger again, right? Stronger, weaker, stronger for the magnetic field too. They are kind of moving through space. You can see that. So on the third axis here, they are traveling mutually perpendicular. All three of those things are perpendicular to each other. So the changing electric field is perpendicular to the changing magnetic field, is perpendicular to their velocity, okay, their direction of propagation, we would say. And so what do we have here? Well, we have a wave. Do you need a medium for these waves to travel? No. Electricity and magnetism work in outer space. They work in a vacuum. Aha. Okay. So what seemed like a small nitpick turned out to be a physics revolution. Okay, so what? Any accelerating charge, because an accelerating charge produces a changing electric field, which will produce a changing magnetic field, which will produce a changing electric field. So any accelerating charge will produce some sort of electromagnetic radiation. Okay. Now, here are the predictions that were basically made. Again, all he's doing at this point is math. Literally, he's doing math. He took wave equations, applied them to electricity and magnetism, and got all these predictions. Turns out all of them were correct. Okay, so again, electromagnetic waves produced when any charge accelerates. Now, if the charge's acceleration is within periodic or just repeating motion, right, basically vibrating up and down or circular or whatever, but some kind of motion that is repeated, then the frequency of the wave will be the same as the frequency of the motion, right? So if something is vibrating up and down at 500 hertz, then the frequency of the wave it produces will also be 500 hertz. Now, here's a prediction that he made purely based on math. He actually just used constants. He used the Coulomb's law constant and then a similar constant, but for the magnetic force, okay, which we haven't learned because it's a little beyond us, okay? But he essentially took them and worked out that all electromagnetic radiation travels at 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. He was actually a little bit above, okay? It's still rounded to 3. He was a little high on that, but this actually boiled down to the constants not being as accurately measured as they are now today, okay? He also predicted that the universal, because it's a wave, right? Universal means applies to all waves, that wave equation that you might remember from physics 20, that still holds. It still applies. And again, because of our third hand rule, because of our understanding of electricity and magnetism, the electric field and magnetic field are always perpendicular to not only each other, but also to the direction the wave propagates. Remember, propagates just means travels. Now, again, if they're waves, they should behave like all other waves, okay, with the exception that now they don't need a medium to travel through, but they're still waves. They're still a carrying of energy, okay? Behaves as all transverse waves do. In other words, they should interfere, reflect, refract, diffract, etc. Now we start to see, okay, now we've explained Huygens and Young's experiments without the problem of how do they get through space. Now, here's one that was seen as a pretty big deal, right? This may be kind of a whole new world for you, of at least for things to study and learn, okay? But that is that there are other types of electromagnetic radiation other than just light. Other than just the light we see, there is probably, Maxwell predicted that there should be different types, but of course we can't see them because they're not visible light. Now, it's worth mentioning here, actually, that Maxwell didn't really know he was even talking about light. Maxwell was just trying to kind of unify Oersted and Faraday. He was taking this electricity and this magnetism. He was kind of unifying it with math. And again, out of that math, he used those constants that govern electricity and govern magnetism. Since he was unifying them, he put them together. And that's how he figured out the speed that a wave like this, his electromagnetic wave, would travel. When he worked out that speed and he got that number, 300,000 kilometers per second, there had been experiments that we'll look at in the next topic. There had been experiments that had found the speed of light to be very, very close to that, right? Within a few percent. And so Maxwell started out just unifying electricity and magnetism. When he got this speed, he said, that can't be a coincidence, right? I think light is an electromagnetic wave, okay? And so you kind of see how he was just looking at electromagnetic waves, saw all these different possible values it could have, and said, hey, light seems to fit this perfectly. So I think there's a whole bunch of electromagnetic waves, and I think light happens to be one of them. Right? Of course, he was correct. Let's really quick take a look and just get our foothold on this idea of accelerating charges and whether they produce EMR or not, electromagnetic radiation or not. Okay, so it says that, the question says, an electromagnetic wave is generated in part of this, but not in another part. Okay, that's just kind of information. Is EMR, electromagnetic radiation, produced in the straight portion of the wire? Explain. So again, we have charges moving along, right? They're showing current, okay? So we have a charge moving along, just call it Q, okay? It is moving. Now, in this portion, is it accelerating? Well, no, right? This is just uniform motion. It's just going at a kind of a constant speed here. It's on a flat part of its path, right? So in the straight portion, no, right? Q is not accelerating. Okay, to produce a changing electric field, you need to be accelerating. Now, I know what you're thinking. You're thinking, hey, but it still produces a magnetic field. We learned that last unit. A moving charge still produces a magnetic field. Okay, you're right. That is for a slightly different reason that actually has to do with special relativity. Okay, so special relativity is definitely a modern physics concept. Beyond the scope of this course, but essentially what it means is that when an object is moving, space actually changes a bit from its perspective, and so there would actually be a bit of a charge buildup and yada yada. Essentially, it would feel what from its perspective is an electric field force, right? And we just say, okay, we'll call that the magnetic force, the induced magnetic force. Okay, so again, if that totally lost you, that's okay. It's special relativity is what explains it. Okay, so I don't want you to now go around saying, hey, a moving charge in a wire does not produce a magnetic field. It does. That's still 100% true. I didn't lie to you last unit. Okay, however, it will not produce electromagnetic radiation because its electric field is not changing. Okay, it's moving, but it's not changing. It would need to accelerate for the electric field to be changing. If you're not happy with the fact that it can produce a magnetic field, but it's not producing a changing electric field, well, let me ask you this. What if we boosted our velocity up so that we were stationary next to the charge, right? Well, then we would see it as not moving, right? And so me and you, if you're standing still and I'm moving at the same velocity as the charge, we can't disagree on whether or not it's producing electromagnetic radiation, okay? We have to agree on that. We can't disagree on whether or not it's producing electromagnetic radiation. We can disagree on some things. That's for later physics. There's some things that we have to disagree on if one of us is moving and one of us is not. However, we can't disagree on that, whether or not the charge is producing EMR. So it must be accelerating to produce EMR. If it's accelerating, if I'm moving and you're standing still, it's still accelerating relative to both of us. If I'm moving with uniform motion and you're standing still and it's accelerating, well, then it's accelerating relative to both of us, right? I have uniform motion. It does not. You are standing still. It is accelerating to both of us. And we will both agree that this thing is producing electromagnetic radiation, which is something we have to agree on. Anyway, that is all way over what we truly need. For now, you just need to hopefully accept that it will produce a magnetic field, but not a changing electric field. And so it will not lead to electromagnetic radiation. Okay, is EMR produced in the solenoid? Now that's the curvy part. Is it accelerating here? You bet, right? Remember, circular motion, even if it's a constant speed of circular motion, is it always moving in the same direction? No, right? It's accelerating centripetally. It's accelerating inward technically, right? It is always changing its direction. So to accelerate is to change your velocity. And there's two ingredients to a velocity. There's your speed and your direction. So if that direction is changing, it is definitely accelerating. Yes, direction of V is changing, therefore A does not equal 0. As soon as the acceleration of a charge is not 0, it is producing electromagnetic radiation. Okay, directly on the diagram, identify where acceleration takes place and what direction it's in. Well, there's a few places. Okay, so for example, here, there would be a little bit of EMR given off, right? Because that is an acceleration. It's a sudden change in direction. So acceleration. Okay, here, of course, right, throughout the whole thing, there's inward acceleration. So I'm not going to draw them all, but right, there's always kind of an inward acceleration. So throughout the whole solenoid, acceleration does not equal 0. Okay, and so EMR would be produced. Of course, again, here, same idea, changing direction, right? Remember, even if it doesn't speed up or slow down, change direction, boom, that's all you need. It's accelerating, okay? And obviously here as well. Now, where would you apply the following physics principles? So 0, 1, or 2, just to remind you, 0 is where F net is 0, which by extension means acceleration equals 0. Physics principle number 1 is when F net equals ma. In other words, when F net is not equal to 0, and therefore A is not equal to 0. Okay. Physics principle number 2 is when we have circular motion, uniform circular motion. So acceleration equals centripetal acceleration. Okay, so again, it's accelerating. So where would we use them? Well, here, okay, on the straight portion of the wire, that's definitely uniform motion. So here I would have physics principle 0. Same goes here and over here. Okay. In here, I mean, take your pick. Really, physics principle number 2 is just a fancy application of physics principle number 1. So physics principle number 1 or number 2, I mean, it's going to depend on the question which one's going to be more useful there. Of course, here, right, that's physics principle number 1, where acceleration does not equal 0. Same goes there. Okay. So the kind of brief history of the electromagnetic theory, what Maxwell changed about it, and why that was a big deal. Okay, with the big idea being that an accelerating charge produces electromagnetic radiation. What is electromagnetic radiation? Well, electromagnetic radiation. Radiation means it radiates out, right? So electric and magnetic fields radiating out from some source, and they do not need a medium to travel through because they are what keeps themselves going. A changing electric produces a changing magnetic, produces a changing electric. Okay, so that's it for that topic. If you're looking for practice, check the Google Classroom or the agenda for which questions kind of go here.